You want me to start?
All right, let's go ahead and get started. For those of you that are interested in receiving this or watching this later, Ted is actually recording all the sessions, and you can buy a copy of this session or any session that you want to watch again or missed outside by registration. Also, I have a few pieces of swag to give away. Is anybody interested in a few ShmooCon little pouches? Oh, yeah, dead spot. I also have a water bottle for a trivia question. Who can tell me the company that the Shmoo group was working with when it was founded?
Last internet.
All right, there you go. All right, let's go ahead and get started with the session. This is Eliminating Timing Side Channels by Peter Schwabe.
Thank you very much, and thank you for having me here. I guess that some of you people have been at the talk by Dan and Tanya yesterday, and I see at least Dan in the back, and I saw Tanya before. So they gave a little bit of a forward reference to this talk, and maybe occasionally I will give some backward reference to the talk yesterday, but if you haven't been there, it's not a problem at all. So let me just start by a short motivation. And well, if you look at crypto research over the last few decades, then this research has produced some algorithms that we're reasonably confident in, and that I would assume most people here in the room would consider secure crypto. So one example is the AES-256 block cipher. That's what I'm using to encrypt the hard drive of my laptop, for example. And okay, block cipher by itself may not be sufficient for like doing real crypto, so you want some mode of operation, you may want authenticated encryption. So let's say AES-CBC with HMAC SHA-256. And if you're a bit more paranoid about the hash function, you use SHA-512 or you use SHA-3, doesn't really matter. And then when we look at public key encryption, we might want to use something like RSA-2048. Encryption signatures. Some people don't like RSA that much. They may want to go for elliptic curves. So just an example, you could use ECDSA signatures with a SecP256K1 curve. That's what you're using if you have bitcoins. Now, none of these primitives are my favorite, but it's reasonable crypto. I mean, if you have an advertisement listing one of those, then you feel like, yeah, that's probably kind of okay. For each of those would be probably for encryption something like Salsa 20 with Poly 1305, and then use curve 25519 and add 25519 signatures for various reasons. But the reason that I'm listing those is the next slide, because Dan was already mentioning yesterday that AES-256, this pretty high security block cipher, an implementation of it in Linux, the mcrypt hard drive encryption, was broken in 2006 in just 65 milliseconds by Osvik, Shamir, and Tromer. And they managed to recover the secret key, 256-bit, high security. In 2013, there was this attack named Lucky 13, which broke the CBC mode encryption together with authentication in the way that it was used in TLS in pretty much all TLS implementations. Now, they didn't get the key, they recovered plain text, but that's bad enough. And when we come to public key encryption, then RSA-2048 in GNU-PG 1.4.13 was successfully attacked by Yoram and Faulkner in 2014. And what they said is that on average, the attack is able to recover 96.7% of the bits of the secret key by observing a single signature or decryption route. And finally, when we look at ECDSA, then there was another paper in 2014 by Banger, Van der Pol, Smart, and Yoram. And they said that they have a reasonable level of success in recovering the secret key for OpenSSL ECDSA with the SecP256K1 curve with as little as 200 signatures. And if you go beyond 200, if you go for 300, then it's actually really reasonably high, even higher level of success. Now, what those attacks have in common is that they all don't break the math. So if you look at this crypto in a mathematical context where attackers can see, maybe control inputs and outputs, and that's it, well, none of these attacks do that. What these attacks do is that they get additional information. So what they do is, well, what I want to use as a topic of this talk are timing attacks. And the general idea of a timing attack is fairly easy. So the general idea is that you have some secret data, typically the key, that influences the timing of the software. So influences how long the software takes to carry out the computation of the secret data. And an attacker measures this time and then computes the, well, influence to the -1 and obtains the secret data. It's often not quite as simple as just that. I mean, getting back from the timing information to obtain the secret data is maybe some serious computation. It's not that easy to get high-resolution data, timing data in the first place, but that's the basic idea. And that's what all these attacks before used, and I mean, 65 milliseconds to recover an AES key is pretty scary. Now, what makes these attacks special in the context of side-channel attacks? So they are a special class of something broader, which is called side-channel attacks, where an attacker observes something additional to, well, inputs and outputs. It could be power consumption of a device, it could be electromagnetic radiation, it could be sound. But timing attacks are special because they can be carried out remotely. And when I say remotely, I mean remotely in two different senses. So one sense is that maybe the attacker needs to run software on the same machine as this cryptographic software. And well, this may be that he has an SSH log into the same machine. Maybe he has just a different virtual machine running on the same hardware. But the thing is that the attacker can sit somewhere else in the world, can just log into that machine and carry out the attack. And in some contexts, remote has an even a meaning which goes even further, namely that the attacker doesn't even need an account on the target machine. The attacker just sends data to some service running on this machine, and, well, gets some answer back and just measures the delay over the network. And, well, that's obviously a different kind of remote, so this is what's typically called a remote timing attack. But the point here is that unlike for all other side-channel attacks, timing attacks you cannot avoid by just taking a server, putting it in a room, and locking the door. If you do that, then a power analysis attack, you just won't get close enough to measure the power. Or electromagnetic radiation, typically you need to get really close to the device to pick this up. But timing attacks, they're remote. So they're really scary. And they're not only scary for something like smart cards, which you give in the hand of the attacker, but they're scary for laptops and for servers. Now, let's look at the reasons for timing attacks. And here is the first reason. So the first reason is that you have a branch which says, well, if a secret bit is set, then we do something, so do A, and otherwise we do something else, do B. And this is something which, if you explain this even to non-experts who have never programmed before, they will understand that, yeah, this is a problem. I mean, if A takes a different amount of time than B, then this whole thing takes a different amount of time depending on the secret bit. You measure the time, you get the secret bit. It's pretty obvious. However, there is two questions that arise, and in the next few slides I want to explain what these problems are. One problem is, well, what happens if A and B actually take the same amount of time? And the second thing is, how do we avoid this problem? And in order to do this, I want to look at one example, which is sort of the classical example of exactly this kind of code in a cryptographic context, and that is exponentiation. Now, exponentiation is something that you find in RSA, decryption. You compute A to the D mod n, where D is the secret key. And, well, A, D, and N are all very large numbers. And you find some very similar operations, no matter whether you use El-Gamal or DSA or ECC. So pretty much all state-of-the-art asymmetric public key cryptography. You end up doing some computations roughly like that. How do you do this? Let's look at an example. So let's say we have the exponent 105. Now, one thing that we can't do for really large numbers is just compute A times A times A times A times A, D times. If we do that, then an attacker could just do that and break the whole thing. The problem is just D is too large. So this algorithm would be exponential in the length of D, and we don't want that. We want something polynomial or actually linear in the length of D. So we write down the exponent, and we write down the binary expansion, so like that. So 2 to the 6 plus 2 to the 5 plus 2 to the 3 plus 2 to the 0. And let's just write in all the 0 bits as well. That looks like that. And then we apply Horner's rule. So we just write that, well, first we take 1 times 2 plus 1, and then times 2 plus 0, times 2 plus 1. So we always do times 2, and then depending on whether we have a 1 or a 0 bit, we add 1 or we add 0. And then we can move the whole thing to the exponent, where all the times 2 become squarings, and all the plus 1 become multiplication by A. And the plus 0 become multiplications by 1, which, well, don't really matter. So if we do that, then we end up in this case here with 6 squarings and 3 multiplications. And if we do that more generally for any exponent, then we get 1 squaring per bit and we get 1 multiplication per bit, which is 1. Okay, let's look at some code which does that. So here's some C code. And this does square and multiply. Now, usually, as the comment says, you want to do that with, well, big integers, like 20, 48-bit integers. I just reduced that to 32-bit integers because then I don't need any libraries and you can just grab the code and compile and it actually works easily. But the idea is exactly the same. So you go through the code and, well, you have an exponent which in this case has 4 bytes because, well, it should be about as long as A and the modulus. And then you go through the bytes first of the exponent, then you go through the bits of each byte. And then if for each of the bits you square, so that's this r times r mod n. And then if the corresponding bit in the exponent is set, then you multiply by a. And then you compute modulo. Now, well, this is obviously not constant time, right? I mean, for every 1 bit we have a multiplication, and so just measuring the overall time, you already get the number of 1 bits. And if you can measure maybe in between, because you have an attack process which is in between somewhere, you get the secret information that you want. There is a fix to this, which is called square and multiply always. And there's multiple ways of writing it. Now, I chose a way here which is a bit tricky, but it illustrates what I want to do in the following. So what we do here is that in each step, we square and we multiply, and then we decide whether we want to use the value that has been multiplied. So we say if the bit is set, then we multiply and store the result to r, and otherwise we just multiply and store the result to t. And, well, t is not used. So this is the bit tricky part because if you throw a compiler at that, the compiler will say, oh, wait a second, this variable is never used, I probably don't really have to do this computation, and then you're in trouble. But we can avoid that. And there's a very easy way to avoid that, that is, don't use C, use assembly. I didn't put that on the slides because it's a bit hard to follow, but in principle you can do that. I mean, you just write the whole thing in assembly and then the compiler can't screw up. However, what I want to highlight here is another problem. So now we have 2 operations that, if they're carried out, let's assume we do that in assembly, we don't have a compiler doing funny stuff there, and those are exactly the same operations. Right? We have a modular multiplication, we just have different arguments. And we have a branch around this. So is this safe or is this not safe? Tricky question. Generally, it's not safe. And there's 2 reasons for this. One reason is that pretty much all modern CPUs have branch prediction. So the CPU will guess what it needs to do, and if it guesses right, then, well, it's slightly faster, and if it guesses wrong, it will be slightly slower. The other reason is instruction caches. So it may be that the instructions of the one branch are in cache, the ones of the other branch are not in cache, and then depending on which of the 2 branches you take, again, you have a timing leak. There are some architectures where this is actually safe. So for example, if you have an 8-bit AVR microcontroller, very, very simple architecture, there is no branch condition, there are no caches, and you can balance branches this way. Generally, it's a bad idea, and even on the AVR, it's tricky to do, easy to get wrong, and very hard to check afterwards. So this is not safe. So what do? What we need is we need a conditional statement, but without an if, without a branch on the assembly level. In other words, we want to rewrite this. So this is pseudocode, and this is pseudocode for the most general kind of a conditional statement. So you can imagine that A and B here are some routines that modify a large data set, and this large data set is R. And then either, well, all the output of A is stored there, or the whole output of B. So you can write every branch like this. How do we replace this? We replace it like this. So we assume that we have this one bit, which is S. It's either 0 or 1, so this really must be a bit. And then we just say we assign to R S times A plus 1 minus S times B. This is purely arithmetic, and it's safe. There is no branch in there anymore. So if you remember any slide from my talk, then remember this simple formula of how to get rid of branches. If you do that in practice, you don't really necessarily want to use multiplication or addition. You can do that with XORs and ANDs, and I will have some C code on the next slides showing how that works. The interesting thing about this is that if you have very fast A's and B's, so something where you really just do an assignment, This may even be faster because, well, it's just a little bit of logical operations in the end, which can turn out faster than a branch. However, if A and B are both routines that take fairly long, then, well, you have to compute both, which is exactly what a branch would avoid, but there's no way to get rid of this. I mean, you have to do both, otherwise you leak timing. Okay, so let's fix the square and multiply always. So what I do here, and this, by the way, also fixes the problem with compilers screwing up, is that, so first we do the squaring, we do that any time, and then we compute this t, which is, well, a times r, and then we say, well, if the bit is set, then we do conditional move from t to r. And now, I said before that we need this bit to be 0 or 1, so what I'm doing now here is I take the exponent at the position, I mask out the corresponding bit, and then I move it just to the rightmost position so that I really have either 0 or 1. And now the question is, what does this CMOF look like? Well, it's exactly what I had on the previous slide. So the conditional move, depending on the bit b, looks like this. For example, you first get b equals minus b. So now in 2's complement, assuming that we have 2's complement, which we typically have, b is either 0 or all f. So you have a mask, which is either 0 or f. And then you just, well, XOR r and a, and you AND that with b, and then you compute r XOR this temporary variable t. So now t is either 0, in which case the last line won't do anything, or r is r XOR a, which will exactly store a in r. And this is purely arithmetic, and the compiler won't screw up here, typically. It must be a very, very smart compiler. I haven't seen such smart compilers. And this is constant time on any architecture that I'm aware of. Okay, so this is how we eliminate branches. How about the problem number 2? This is a bit more tricky. So here is problem number 2. If you access memory at a secret location, so you can think of it as star secret or just as table at position secret. So some memory location at a position which depends on a secret bit. That is a problem. And the most famous example of why this is a problem is the advanced encryption standard. And this is, by the way, also the reason that the advanced encryption standard is not one of my favorite algorithms. For those of you who are not really familiar with AES, I guess everybody here has heard of it. It's a block cipher that Ryman and Dahmen proposed in 1998 and was selected at the advanced encryption standard in 2000 by NIST. And it has a block size of 128 bits and, well, some state, 4x4 matrix, and different key sizes. So on the first slide I had this 256-bit keys, and processes the state through several rounds, and in each round it involves a round key, and it performs several operations: subbytes, shift rows, mixed columns, and add round key. Now when you have an introduction to crypto lecture and the AES gets introduced, this is what you see. And then, who here in the room has implemented AES in software? 1, 2, yeah, so a few people have. And so when I first looked at AES software, I somehow didn't see this. I was really confused. It was software written by Dan, which didn't quite help. Because he was my PhD supervisor at the time, I didn't really dare to ask about it. So the tricky thing is that the way you implement it in software traditionally doesn't really show you these 4 operations per round. And this actually comes from the proposal, from the original AES proposal, in which Dahmen and Ryman said how you should implement AES on 32-bit machines. And it was in fact designed to be efficient on 32-bit machines through this implementation technique. And what they said is that the different steps of the round transformation can be combined in a single set of table lookups, allowing for very fast implementations on processes with word lengths 32 or above. Now, table lookups, that's exactly what I said before, is a problem. So here is one round of AES. So what happens here is that you have an input which is, well, the state, and the state is written as 4 32-bit words, Y0 to Y3, and the output is again 4 32-bit words, Z0 to Z3, and okay, there's the round keys, and this is round number 1, where, so you take the 32-bit words, you take out the bytes of those and use them as lookup indices into tables T0 to T3, and then, so you take 4 words, you XOR them together, and then you XOR the round key, and then you're done, and you do that for Z0 through Z3. Now, obviously, what happens here is that we have a lookup at Y0 shifted by, well, 24, so some byte of Y0, And y0 was before computed in the first round by just taking, some input block XORed with a whitening key. So it's something that the attacker may know or control XORed with the key. So y0 is about as secret as it gets. How would we attack that? Well, the most plain attack that you can think of this is an attack that works as follows. So assume that AES has been working for a while, has been doing some encryptions, and all these tables, now the example is T0, but you can think of this also for the other tables. All the tables are sitting in cache on the computer. And now the AES and the attacker's program run on the same CPU, so they take turns in running. And now the attacker's program just loads some data and kicks out some of the table entries from cache. Now it's AES turns again, and now the attacker doesn't really know what's in there. I mean, it could be that AES has, again, loaded from those table entries and replaced data in cache again, or, well, maybe not. So the attacker now loads data. And if this is fast, then the attacker gets a cache hit. So his data was still in cache, meaning that the AES didn't replace this cache line. And if it's slow, then there was a cache miss. In other words, AES just did load from this cache line. So, well, the attacker measures the time and learns something about whether AES loaded from this cache line. Let me generalize this. The general statement is that if you have a load or a store, it's also true for stores, that depend on secret data, the address depends on secret data, then that leaks timing information, which can typically be exploited by an attacker. Now that's more tricky. I mean, I already told you that branches are a bad idea, and if you tell a programmer you're not allowed to use if statements, that's pretty serious. But if you tell a programmer you're not allowed to use if statements and table lookups, that's even worse. So what do we do here? And the interesting thing is that there is something which is often considered a countermeasure to this. And this countermeasure is that you observe that in this attack, the attacker doesn't learn the whole address. What the attacker learns is the cache line. So now maybe if we just change the whole table layout such that, well, the address is secret, but the cache line is public, so we only look up stuff from within one cache line, then according to what I just showed you before, this should be safe, right? Well, or not. Tricky. There was a paper in 2005 by Dan, and Dan looked at, well, exactly timing attacks against the AES. And while he was discussing this as a countermeasure, and asked the question, does this guarantee constant time S-box lookups? And the answer is no. Pretty much in parallel, a bit unclear how the history goes there, there was a paper by Osvik, Shamir, and Tromer, the one that I mentioned before, the one with the 65 milliseconds. And that paper also looked at countermeasures. And they also looked at this countermeasure. And they said that this is insufficient on processes which leak low address bits. And both papers also explain some reasons why maybe the processor may leak those low address bits. And some reason is that there may be cache bank conflicts. So depending on whether those values and this value end up in the same cache bank as another recent store or something like that, there may be slight timing variations, and, well, maybe an attacker can exploit those. There may also be failed store-to-load forwarding. So if there was a recent store to some space in memory, then the CPU will try to forward that store to a load afterwards if, well, the addresses are the same. Except that the CPU doesn't look at the whole address, that would be too expensive, so it looks at the last 12 bits of the address. So if there's a store before which has the same last 12 bits as the next load, the CPU will first assume, yeah, okay, so I can forward that. And then it looks at the whole address at some point and says, oh, wait a second, I was wrong here, so let's do the command back. So let's just flush the pipeline here and go back. And that, of course, also takes time, and that influences the timing. So this is not safe. And at this point, that would be really good ending for this slide. I mean, I could just stop here and say, you know, it's not safe. But the situation is more interesting. And interesting in the security sense doesn't mean good. So, for example, you see that OpenSSL is using exactly this countermeasure in, I think, various functions. One of the functions is the bn-mod-exp mont const time. So it's doing some modular exponentiation. It's using a slightly advanced version of, well, actually quite advanced version of the algorithm that I showed before, which pre-computes some stuff and puts it into a lookup table. Obviously, then you look up from this lookup table, the lookup indices are secret, and you're in trouble. So they changed the layout of the lookup tables exactly by, well, laying it out in cache lines. And they claim that this limits the amount of timing information by I don't know how much, and it's called constant time, although it's probably not. Then Brickell from Intel at just 2011 gave a talk, and he basically said, yeah, that's kind of fine, that's an okay countermeasure, that should be good. And well, then Dan and I in 2013 in the RUM session of chess, we wrote a small program that demonstrates that no, it's not fine. Now this was a program which really wanted to just illustrate the effect, so it's not an attack against any cryptographic implementation, it's just something which illustrates that if you load from different positions within one cache line, this takes a different amount of time. So sort of the big to-do here is attack OpenSSL. And this is really still on the to-do list, hasn't happened. And I think if you want to convince people that this is not a good idea to use as a countermeasure, well, probably this has to be done at some point by someone. So, if I say that this is just a countermeasure, then how about a countermeasure? And I can tell you this countermeasure is kind of annoying. So, the countermeasure is that you just go through the whole table, you load each entry, and then you say, have I reached the entry that I really want? And if I have this entry, then I just use the CMOF function that I showed before to just copy it to my result. So in other words, I'm just comparing whether I've already reached the right position, and save that in a bit, and then I'm using CMOF afterwards. Does that look like constant time to you? Very good answer. So this doesn't look good. Don't do this. Well, it may work. It depends on the CPU. So it also depends on your compiler. So this is something where you tell the compiler this is actually a Boolean value. And Boolean values are the kind of things where the compiler thinks, hey, that's cool, I know Booleans, I use them for branches. So maybe that's not the right thing to do. So what we want here is something called is_equal, which gives you, well, the same result, but does that in constant time. And here's an example of what is_equal looks like. So just if you think like this equal, you rewrite that in a constant time way. What I decided to do here is to make that slightly more general than using just u in 32. I mean, this one is just comparing to u in 32s, but the approach of this function works for any data type. So what we're doing here is we're iterating over all the bytes of the data type, and we're XORing the bytes, and then we're ORing up this result into R. So R is initialized with 0. So if the two values are the same, then in the end R is 0. And then we just compute R equals minus R, which again gives us either 0, or it gives us all ones, or FFFF. And then we just shift that such that the highest bit goes to the lowest position, and then we return 1 minus R. So this is a constant time version of is_equal. And now you maybe realize that when I teach my students how to write constant time code, and then I ask them in an exam, like that this very small line of just equal requires that amount of code, they typically screw that up. And actually, it's not just my students. It's quite a few people who screw up constant time code. But this kind of works. Okay, so how about back to AES? Now when I show this, then you might ask, wait a second, if AES, if you implement it straightforwardly as the proposal tells you, is highly insecure, then why was AES chosen? I mean, if you can't really properly implement it in software, why would anyone want this? And there is some discussion about side channel attacks in the final report. And the final report says that table lookup, not vulnerable to timing attack. Relatively easy to effect defense against power attacks by software balancing and so on. But at the time, people really believed that table lookups are not a problem. I talked to about this with Johan Dahmen, one of the two AES designers, and I asked him, so if you were to design AES today, would you still do it the same way? He said, no, definitely not. And at the time he said, we really believed this. Which is a bit funny because Paul Kocho's paper on side channel attacks mentioned this as a potential side channel already a few years earlier. But at the time nobody had really demonstrated this effect. So what now? When we have AES, we kind of have to live with it, we have to implement it. And if we do it a straightforward way, it's highly insecure. Well, you can do this table lookup technique that I showed you before, but if you do that, then for AES, that's horribly slow. I mean, it's pretty large tables, and if you just go through, for each of the entries, you go through all the entries, and then you use this horrible is equals function, it's not a good idea. It's really horribly slow. So here's Intel's answer. People screw up in software, let's just do it in hardware. So they added AES-NI from Westmere. So now when you have an Intel processor, you use AES-NI. That's the best thing you can do. And here's ARM's answer. Yeah, people screw up in software, let's better do it in hardware. So from ARM v8, there are the crypto extensions. So if you happen to have an ARM v8, or well, get one in the near future, then if you need AES, you use it in hardware. But there's still some processors out there that don't have this, like my smartphone, for example. And I have a few older laptops that are before Westmere, so I don't have AES-NI. So what do you do on those? Well, there's essentially two answers to this. And one answer is that you can use AES with vector permute instructions. And that was presented by Hamburg at CHES 2009. So if you have a fast vector unit, and you can permute items in these vectors, then you can use that to implement AES. And depending on how efficient these permute instructions are, and depending on how powerful they are, this can even be pretty fast. There's another technique, and this is a technique which is way more general. You can use that to protect any algorithm against timing attacks. And you can use that actually to implement any algorithm, and that's bit slicing. And I will show bit slicing on the next few slides. It was originally proposed by Beham in 1997 for the data encryption standard. And then there were afterwards several papers doing that for AES. There was Matsui who did a lot there. And the implementation in OpenSSL. So OpenSSL also has an implementation of bit-sliced AES. That's by Emilia Kasper and by me. So what does bit slicing do? Bit slicing is a tricky thing, and I'm not convinced that you can explain that on slides. I will still try. So I've tried this several times and then afterwards discussed with people, and I got this impression that they did not understand it. And maybe the thing is just that you have to sit down and write some bit-sliced code, and then afterwards, at some point, it makes click and you understand how it works. Now let me try. I actually do have some code that afterwards you can look at and you can compile. That's on the next few slides. So imagine that you have registers that have a length of only 1 bit. And now you have to work with those. So what can you do with 1 bit? Well, you can do something like XORs of bits, you can do ANDs of bits, you can do ORs, maybe you can do NAND. So you do bit logical operations on these bits. And that's essentially the same as a hardware implementation, right? I mean, you take the bits and you put them through gates, and the gates now just simply become instructions, so XOR whatever instructions. So you think a hardware implementation and you just implement the whole thing in software. But, well, our registers are kind of a little bit longer than just 1 bit, so we're throwing away a lot there. But now if you think that you have many independent computation or data streams that you want to compute on in parallel, you just put them in the independent bits of the register. And then whenever you do an XOR, you don't do that on just 2 bits, but that you do that on 2 vectors of 32, 64, 128, 256 bits, depending on how long your registers are. So you kind of do your hardware implementation, but you do it in parallel on many independent data streams. That works for any algorithm. I mean, as long as you have XOR and AND, for example, you can do that for any algorithm. The performance very much depends on, well, what your algorithm looks like, what your architecture looks like, how long your vector registers are, or your registers are, how efficiently you can do bit logical operations on those. And it depends on the amount of data level parallelism that you have. I mean, if you have, say, 256 independent data streams, great. Then you can do that and it may be quite efficient. If you have just 1 data stream, then you end up just putting it into the first bit of each register, which is not going to be very efficient. Okay, so let me just give an example of this. I can't give the whole example of the AES, that would take a bit too long. But arithmetic inside AES is based on, well, essentially arithmetic on polynomials, on binary polynomials. So a binary polynomial I have up here of degree 4. It's just something like a3 times x to the 3 plus a2x squared plus a1x plus a0, where all the coefficients are either 0 or 1. And arithmetic on those coefficients means if you multiply them, then it's a logical AND. If you add them, it's a logical XOR. Okay. So now, I have in C code, I have a poly4, which is exactly such a binary polynomial of degree up to 4. And so the 4 coefficients are just in the low 4 bits of each byte. And then I want to have a data type which does that 64 times parallel independently. And this will be our bit sliced representation. And here's a function that bit slices the data. So it gets as input 64 independent polynomials and outputs a bit sliced, 64-way bit sliced polynomial. And you can think of this as just a transposition of bits. So if you think about the whole state as a matrix, it's just a transposition. So you just go through the bits, you mask out a bit, and then for the polynomial at position I, you just set that at the positions I in those unsigned long-longs here. And while you have 4 coefficients, so you put that in, well, each of those 4 unsigned long-longs, you put one of the 4 bits. This code actually works, I think, I tested it. And then you can afterwards perform arithmetic on those. That's what it looks like. So if you multiply, say, 2 of those polynomials, well, you get as input 2 such polynomials, so poly 4x64, and then if you multiply those, you get a polynomial of degree, so sorry, it was not degree, it was 4 coefficients. So now we get a polynomial with 7 coefficients afterwards. And that's what it looks like. So all the multiplications become ands, all the additions become XORs, and then you just have a straightforward polynomial multiplication. And this is not that many bit operations, and it performs 64 multiplications in parallel. So this may actually be quite fast. Is that all? So far, the lesson that I kind of tried to convey here is that you should avoid all data flow from secrets to branch conditions, and all data flow from secrets to memory addresses. And this can always be done. I mean, I showed you the 2 generic transformations that you can use, but the cost highly depends on the algorithm. In particular for lookups, this may be really, really annoying. But if you do that, then you can afterwards test that this works. And one way to test this is that you use Valgrind. Everybody familiar with Valgrind? Yes. Yeah, okay, good. So you run your code in Valgrind, and you just don't initialize your secret data. And that means that whenever you look up from memory, and the address is uninitialized, then Valgrind will complain, because this may typically be a memory error. And if you branch to somewhere in the code, depending on uninitialized data, Valgrind will complain, because this is typically also a real problem. I just have a small demonstration of this here. So what I wrote is a code constant time test. And it looks like this. So what I'm testing here is the function cryptoscalar mult. That is actually a function from salt, or in this case from tweetsalt, so from this short re-implementation of salt. And the secret in here is the scalar. And up here I have, well, I'm allocating it, but I'm not initializing it. The input, the other input, the public input is initialized just with some random data. Now what is important here is that you really clear up all the memory in the end, because otherwise Valgrind will just complain no matter what. So you first clean up your whole program for Valgrind, and then afterwards you run this kind of test. So if I run this test, okay, it compiles for a short time. Valgrind, and Valgrind will run, and it will not complain. So it afterwards has 0 errors from 0 contexts. So there is apparently, if what I'm saying is true, there is no problem in the cryptoscalar mult function. Now if I edit tweetsalt a bit, and I go to this part of it, so this is essentially doing the conditional move that I showed before, and you see here there's a little bit of an AND with C and then some XOR happening. And I replace that with something with an if statement, so this part here. And I compile again. I run Valgrind again. Then I get 502 errors from 2 contexts. And the errors are exactly what I would expect here, namely that it's a conditional jump or move depends on uninitialized data. So this is not a complete guarantee, because this is a dynamic checker. So it runs through the code, and all the code that is executed it will check. But there could be, well, depending on how you wrote your code, it could be that some parts of the code are just not covered, or some branches are not covered by Valgrind, depending on your inputs. For this code, it's reasonably easy to do that. And it's definitely better than doing nothing. Static analysis tools as far as I know, don't exist yet, but I know some people who are working on that. But now let's assume you've done that. You've transferred all your code and you've protected against timing attacks and you've tested with Valgrind. Are you good? Here's what Adam Langley said about that in 2010. So he wrote that in order for a function to be constant time, the branches taken and memory addresses accessed must be independent of any secret inputs. That's assuming that the fundamental processor instructions are constant time, but that's true for all sane CPUs. That sounds pretty good. Here's what Adam said 3 years later. So the argument to the diff instruction was smaller, and diff on Intel takes a variable amount of time depending on its arguments. Now that tells us two things. First of all, Intel doesn't have sane CPUs. And second of all, we need to pay attention to more than that. But it's not much more than that. So really there is, on various CPUs, there are some arithmetic instructions that are just not constant time. And, well, some examples are exactly this diff instruction, and there's idiff, there's fdiff, on pretty much all Intel and AMD CPUs. They just take time depending on the arguments. There's various math instructions that you don't use for crypto anyway, like sine and cosine. More interestingly, on PowerPC CPUs, there's a multiplier that takes non-constant time. That's tricky, because if you implement, in particular, asymmetric cryptography, and you have these multiplications of big integers, you kind of want to multiply. And, well, this is not safe. And similar on the ARM Cortex M3, there's also a 32 by 32-bit multiplier producing a 64-bit result, which is also not running in constant time. So maybe the safe recommendation here is just avoid these instructions, which can be tricky. On ARM Cortex M3, you have an alternative. There's a smaller multiplier, which is also faster, so maybe it's not such a bad choice anyway. If you don't have any option to really eliminate those instructions and just completely avoid them, really make sure that you know what's going on. Make sure that your inputs always have the right size, that understand really what those instructions are doing, and hope that it's completely documented. Okay, to conclude my talk, here are some references. I hope that they're exactly in the order that I showed them in the talk. So there's this very impressive paper by Osvik, Shamir, and Tromer from 2006. Then the recent papers on various timing attacks that I had at the beginning. Then there is the 2005 paper, the first paper on cache timing attacks on AES by Dan. By Ernie Brickell from 2011, that's the slides from his chess talk. And then we also have the slides from our word of warning talk from 2 years later from chess online. And finally, there's the paper by Mike Hamburg on this vector permute instructions. And there is the fast new software DAS implementation software by Biham, which was the first paper, as far as I know, to introduce bit slicing. If you want to know more about these kind of things and you want to contact me, the easiest thing is you just go to cryptojedi.org. That's my website. And thank you for your attention. Are there questions?
Yes. I was. So when I was why do you time that sort of good or that? Why can't you use her counters? And I can't get it to her, I can tell you which fails that.
So could you say that again? There was.
On a modern CPU, why do you need a timing attack or your parallel programs with registers and that? Why can't you use her counters and just really give the direct intelligence register?
So why I need a timing attack on a modern CPU? Or well, it depends on what kind of access you have. So if you, for example, have you're just a normal user on a CPU, you can log in, then you typically don't have the right to get out what the CPU is doing. If you're in another virtual machine, then you don't get to access what's happening in another virtual machine. Or do I get your question correctly? Oh, you mean the performance counters? Okay, yeah, so essentially what the performance counters tell you is a very, very high resolution information of what's going on here. And you can go beyond timing with this. Of course, if you don't even have an account on the machine, you can't get that. If you don't have root on the machine, it depends on exactly how those are enabled, whether whether it's exposed. It very much depends on the architecture. So for example, on some ARM architectures, you don't even have to have access by default to the cycle counter. So you need to, it very much depends, but yes, there are very, very high resolution ways of getting exactly this information if you have access to it. Yeah. More questions? Oh, yeah.
So, what if you, instead of doing table lookups, just implement the finite field math for AES?
Yes.
Function?
Okay, so the question was, can't we just do the finite field math? Yes, we can, and that's exactly what bit slicing does.
Oh.
You can also do that without bit slicing, but then you typically pay quite a bit in terms of performance because it's a binary field arithmetic. And most CPUs don't have native support for arithmetic in binary fields. Some CPUs do. Tricky. It's very architecture dependent how efficient you will end up. And if you do binary field arithmetic on a CPU that doesn't have instructions for it, the way to typically implement that is through lookup tables. The multiplication at least. And then you're in trouble again. So you need to get rid of that, and then it gets quite slow. So, and bit slicing does exactly that. It's a hardware implementation of the binary field arithmetic. Yes?
Is the assumption that if an adversary does not have the local code execution on the machine that might have an attack is being performed on, that the timing differences in those cryptographic operations that I would be doing would be below the noise floor of network jitter to the point where I've heard people make arguments that it doesn't matter, and I don't like that.
Yeah, so...
Is that a valid assumption?
No, it's not. So it's not a valid assumption that network jitter will just hide your timing. Tanya? Okay, so the question was whether, okay, if you cannot run code on the same machine that is executing the crypto operations, and you're kind of doomed to do the timing over the network, whether there isn't just enough noise in the network delays anyway to hide all of the timing information. Dan and Tanya had on their slides a reference to a paper by Brumley and Tuveri from 2012 from Azorix. It took them a few minutes to steal ECDSA signing key in OpenSSL over the network. So that was a local area network, and afterwards Brumley gave an interview, and he was asked whether it can be done over the network. And he said, well, over a local area network, yes, we did that. Over the internet, will be tricky, but probably yes, if you just get enough samples and filter out the noise. And then he said, would it be, is it possible to steal the key off a Mars rover and take that distance? And he said, well, probably not. But then again, would you want to rely just on network delays when communicating to the Mars rover? So it's tricky. I mean, it definitely gets harder and harder the more noise you have, but if you get more samples, then typically you can filter out the noise and still get some information. So it's not a safe assumption, definitely. There's another answer to this, which is that if you write cryptographic code, you put it in a library, and then you just don't know where it's going to be used. I mean, you can put all kind of comments and warnings in there, and you can say, never use this if somebody is using your code in a context where other people can run code on the same machine. Somebody will grab it off the internet and just use it.
And that's also instruction to the attack. That's instruction to the attack.
Yes, yeah.
So it might not be used.
Yeah.
If I use salt, I'll be safe from all this, right?
From timing attacks, yes. So the last thing that I showed with the non-constant time instructions, I can imagine that on some architectures, for example, the ARM Cortex-M3, if you compile salt, that it wouldn't be constant time. So it's protecting against the two large things that I showed. It doesn't have secret branch conditions. It doesn't have secret memory addresses. We're not systematically protecting against filtering out all kind of strange arithmetic instructions. But for the most prominent CPUs with those problems, we're working on solutions at the moment. Yeah.
So it seems like it should really be on the crypto designer to develop algorithms that don't lend themselves to timing attacks. Is it possible that is it reasonable to expect that you could develop an algorithm where the naive solution is secure against timing attacks, where you're freshman or high school level
Yes.
first coder can implement this securely?
Yes, I would say that it is very reasonable, in particular for symmetric crypto. So if you take SALSA 20, what Dan mentioned yesterday, you sit down, you read the description, you implement it, it's safe. For asymmetric crypto, there's this multiple algorithms that are multiple choices that make it much, much easier, but there's still typically a few traps so typically need something like this conditional move. In at least RSA or DSA or elliptic curve cryptography, something like that. And well, as long as you're aware of how to eliminate this branch, then it's not so hard. Okay. Well, it looks like there's no further question. I've been told that there's 1 more minute left, so that would be a good time to stop then, I think.